All right.
Okay. Hi, everybody. Welcome back to your favorite Wednesday seminar. So thanks for joining us today. And before we get started, just a quick note that if you hear this bell dinging, that's just us signaling the speakers, nothing for anybody else to worry about. Bells are easier than science being held up on Zoom. So that'll be at the 3-minute mark of the talks. So without further ado, let's get started. Our first speaker today is Ralf Ballhausen, and he is a grad student at the University of Erlangen-Nuremberg. He's in the final weeks of his PhD with Jörn Wilms at the Dr. Karl Remes Observatory in Bamberg. His two main research interests are accretion physics of magnetized neutron stars and X-ray spectroscopy of the circumstellar medium and the interstellar medium, including things like neutral and ionized absorption, dust absorption, fluorescence processes, and so on. So without further ado, take it away, Ralf.
Thank you. Thank you for the introduction, and thank you for having me. I think everyone is quite busy these days with Zoom meetings on, and it's the Chandra workshop right now. So yeah, I really appreciate that you take the time. Let's see, can you see my screen? Great. Okay, let me try this again. Sorry, we checked this like five minutes ago or so. So, okay, no, perfect. Okay, so yeah, so my talk will be about absorption fluorescence in the high-mass X-ray binary IGR J16318-4848, which is a supergiant X-ray binary in the normal arm of the Milky Way, and this is one of the most strongly absorbed binaries that we know. And we have observed the source with XMM and with NuSTAR and found signatures of dust absorption, which I'm going to report about. So I'm going to start this introduction a bit more from the dust point of view. So in the paper, we argue strongly directly from the high-mass X-ray binary point of view. But for dust absorption, I mean, all of you know, of course, that dust is very important in terms of absorption and X-ray absorption and scattering in the universe, and the fact that the universe contains huge amounts of dust, and that a large fraction of the heavier elements is actually depleted in dust grains. And one of the most beautiful and like visually impressive evidence that we get from dust is dust scattering halos, where you have a bright background source illuminating a dust cloud or layer between the source and the observer, and then you see a halo of the X-ray scattered by the dust. So this is a picture of an X-ray pulsar taken with XMM, and there you can infer the location of the dust. If we look at the radius of the scattering halo and the delay that the light takes from getting to us, so we can be sure where the dust is located between us and the source, at least if we know some basic properties of what the distance to the source was in the first place, and so on. So we see this around quite a large number of sources, of bright sources. And if we look at the X-ray spectrum, then we also can find signatures of dust, and in particular around absorption edges, because the absorption edges of atoms that are confined in dust grains show characteristic fine structure modulation, because basically when the electron or the atom gets ionized or the photoelectron gets excited, then this wave function scatters by the surrounding atoms, and this produces a characteristic modulation. And this is an example here, just for illustration, of a study by Sascha Segers from ESRON, who looked at Chandra spectra of low-mass X-ray binaries. And this is a close-up of the silicon K edge, where they found also some fine structure modulation, and they modeled this with with dust models, which they constructed from cross-section measurements taken at synchrotron facilities. So they investigated how these fine structures change or depend on the chemical composition or crystal structure of the dust, and built a model for that. So these X-ray fine absorption fine structures are very sensitive to the dust composition and structure. So by really measuring and constraining this fine structure, you get a good probe to measure the properties of the dust. Now, this is just one example, but this has been observed in also a number of sources, and there are many papers of different authors who studied this in great detail. But the question is, again, if you have just like a weak absorption line in your spectrum, you don't know immediately whether this is a source intrinsic feature or whether this is something which is in the just a thin layer of dust in the ISM, so which produces this absorption feature. So you can't really tell where the dust is located. So you might wonder whether this is really a source intrinsic feature, that the dust is in the binary, confined somewhere in the binary, or whether this is basically an unrelated observational feature, which is just because that there happens to be a dust cloud between you and the source. And one way to look at this now, to study, for example, how dust is present in binaries, is now to look at very extreme sources in terms of absorption. And as I told you in the beginning, one of the most extreme cases is IGR 16318. And this is the XMM and new star spectrum. And what you can see is this is probably one of the strongest iron lines you've ever seen in an X-ray spectrum, because the spectrum below 10 keV or so is basically completely dominated only by the iron fluorescence complex. So we don't get any really any soft X-ray radiation below 3 keV. It's just extremely heavily absorbed. And we have this very strong line complex. And this source has been observed a few times, also with Suzaku, with XMM, and of course with integral. And recently also, or not too recently anymore, with Hitomi. So there is an Hitomi observation of IGR 16318, which only had a very few number of photons. I don't recall the exact number. It was more than 10, but less than 20. So really just a handful of photons. And also Hitomi basically only measured the iron line complex with the microcalorimeter. And when you look at these lines and at the strong over continuum absorption and the edge depth, a few of the questions come up naturally. So first of all, you wonder, how do you produce such strong iron lines in the first place? So what kind of absorber geometry do you need in order to make these lines so strong? And then the other question, which is quite interesting to ask, is why the iron lines appear to be very neutral. I think I haven't said this yet, but this is also what the Hitomi observation showed with high accuracy, is that the iron has to be neutral or only very, very slightly ionized. And this is, of course, a bit surprising if you imagine that in order to produce such strong fluorescence lines, you really have to irradiate your absorber very strongly. So you would assume that probably you also ionize a significant fraction of the absorber. And finally, why do these lines have very narrow shapes? So what we see in XMM, for example, is that we basically cannot resolve the line width at all. So in particular, we don't see any strong Compton deformation of the fluorescence lines. You would also expect, if you just look at an absorber which has such a high column density, to absorb all the soft um, radiation, and you process the line photons through this absorber, then you would expect them to be deformed. Um, so we tried first to find a self-consistent gas model to reproduce these strong lines, because what most of the previous um, analysis have done is basically that they model the absorption and the fluorescence independently, such that basically you have an absorption model. There are several absorption models for neutral or ionized absorption. And then you look at what is the residual line flux and try to relate this to each other, but not to really model the emission and the absorption at the same time. So we used XStar, the XStar photoionization code, and ran huge sets of table models where we varied the ionization parameter, the column density, and tried to fitted this to data and tried to reproduce these strong lines. And what we found is that we could basically get the order of magnitude of the line flux correctly, but not really like the exact line ratio or the edge depth. So this is really didn't work out well at all. So the order of magnitude of the line flux is okay, but it's still such a big mismatch that we argue that a single gas absorber doesn't really fit our data well. And the clue there to look, or like the other question about the geometry that is also connected to this is what still this observation or this modeling attempt showed by reproducing the strong line flux is that you need high coverage of this. So you basically need strong or high covering fractions, basically like a spherical absorber. And this is something which has been debated actively in the literature on this source, what the covering fractions are, because also the lines are so narrow. So some people have argued that the covering fraction must be very low and that the average column density consequently must be much lower, because otherwise you would get these Compton shoulders and Compton deformations of the line. But this doesn't really work out too well, because as soon as you reduce the covering fraction and also your equivalent or your effective column density, you get a lot of leakage basically of the weakly or unabsorbed continuum, which dilutes your line flux. So basically, in order to get this line flux to continuum ratio right, you really need to absorb all of the continuum away, such that the line, the residual line is strong enough. So this only works with very high covering fractions, which we've seen from simulations. And then again, it's surprising that the lines still have these narrow profile. And the idea to look for dust in the system now really came from infrared observations, because infrared observations that have been published a couple of years ago show or also report signatures of a strong dust of a large or yeah of a strong dust, in this case infrared emitter, but indicate that there's a lot of dust in the system. And we cannot, with CCD resolution, really resolve the absorption fine structure. So we only have really the edge depth and the line shape and the continuum absorption to look for dust signatures. Nevertheless, we looked at the K edge absorption fine structure, or also edge shape, and this is based on also laboratory measurements by Daniele Organtini, who also measured how these absorption cross-section look like around the edge for different dust species, dust compositions. And this is the example of olivine, where you see basically that this is also has this fine structure which we cannot resolve at the current resolution, which we have. but that even if you smooth this with a CCD response, for example, that the edge will look slightly different. And in red is basically compared what the gas absorption cross-section would look like. So we implemented this in an ISIS or XPEC fitting model and fitted this to the data and basically extrapolated the continuum absorption just by the composition, by the chemical composition of the dust constituents. And what we get is that this actually really reproduces the lines much more nicely. And also in this attempt, we model the fluorescence lines basically simultaneously, in that we look like how much absorption is really through iron K, and by then weighing this with the fluorescence yield and the branching ratios and so on, see what the expected line flux is, and basically use this as an input for the line in our spectral model. So that basically if you increase the absorption, that also then the line or the fluorescence photon would scale up with the iron column. So to go back to this Compton shoulder issue, this is an example where I always stress this is important of another X-ray binary where I see this. GX301-2 is also supergiant X-ray binary, and there this is a Chandra spectrum of the iron line, and this is this Compton shoulder feature which we see. So this has a similar column density, and this is how the iron line looks there. So you have also the very strong K alpha line here, but because of the energy loss of the fluorescence photons due to Compton scattering on their way, you get these shoulder-like feature at the right wing of the line. And although we only have CCD resolution in our IGR observations, we really don't see a Compton shoulder feature that at least is as strong as would be expected for the observed overall column density. And this Compton shoulder feature here is mostly a tracer of the electron density. So basically the hydrogen, the amount of hydrogen that you have, because the Compton, so this is just Compton scattering, and the more hydrogen, or the higher the electron density is, the higher the probability for Compton scattering is. So this is really a tracer, how strong the Compton shoulder is with respect to the primary line is really a strong tracer for the electron density. And in particular, this ratio is more or less independent of any element abundance, because at the point where you do the Compton scattering, the absorption of fluorescence has already taken place. So from the fact that we don't really see a strong iron line, a strong Compton shoulder in IGR, we can argue that the amount of hydrogen has to be much lower than, for example, in comparable cases like this binary. Still, we simulated what the Compton scattering in a dust absorber would look like, and this is basically what we would get out. The nice thing about this simulation was actually we used a bit of an exotic approach here, because we have also in Bamberg a lot of people who do, thank you, a lot of detector simulation, detector simulations for future X-ray missions. And in some sense, this fluorescence line and fluorescence processes and photon escape is like a similar process, which gives you the escape peak in, for example, a silicon-based detector. So we basically use the code which we already developed in Bamberg to simulate this for the X-ray binary. So I'll speed up a little. bit also from these simulations, which we do actually with the detector code, we find that we actually need a really spherical geometry, because these simulations then really include all subsequent self-absorption effects when you produce a line close to a fluorescence photon close to the center of the absorber. It still has to make its way out to the observer, and the chances are high that it gets reabsorbed. So we simulated this again for a large number of iron column densities and found that it really strongly supports the spherical absorber, but with low hydrogen content such that the Compton shoulder is weak. So to wrap up, I think, or I hope I could convince you that to study dust in X-rays is really cool. In fact, really does this great fun to study or to look at if it's not on your bookshelf, of course, and that it is not only a strong absorbing constituent in the ISM, but can also be important in X-ray binaries itself. So like it's also intrinsic absorption inside the binaries. And that it is extreme cases of very high column densities and dense absorbers, that this can also be very important for the production of the fluorescence line flux. It's not only an absorption feature, but it's also important for the modeling of your fluorescence lines. Then for IGR J16318, we are very excited because Chandra is going to observe this source soon, I think, on GOT time. And of course, the Chandra grading spectra will put much more accurate constraints on the actual absorption edge and Compton shoulder flux. And with the upcoming launch of the microcalorimeter missions, so in particular CRISM, of course, next 2 years, and in the more distant future than Athena, we will be able really to resolve the absorption fine structure of the K edge. This is not yet possible with current instruments. There you rely mostly on absorption in iron of the L edge, or for example of silicon in silicon of the K edge, but the iron K edge is not yet accessible, but will be in a few years. And there, of course, we expect a lot more insight in actually the chemical composition and crystal structure of dust absorbers. So I think I'm at the end of my time. Thank you very much for yours, and I'm happy to take your question.
Thank you very much for a wonderful talk. We will take questions now. You can either raise your hand here or put your questions in the chat.
Okay, maybe I have to.
I am not.
Oh no, I should probably keep sharing. I just was looking for the chat box. Sorry.
I don't see anything yet.
Yeah, I don't see any either. I'm also checking the Slack page, though I think most people just put their questions here. Well, it doesn't look like we have any questions at the moment.
That's fine.
You do have, I was going to say, if you do have questions, there is the speaker schedule, but that may have, yes, I think there is some time on it tomorrow as well. So
yes,
if you'd like to talk to our guest today, you can go sign up on the schedule. And thank you again. I'll pass it on to Peter.
All right. So our next speaker is Thaisa Storchi-Bergmann. Dr. Storchi-Bergmann is a professor at the Physics Institute Universidade Federal do Rio Grande do Sul in Porto Alegre, Brazil, where she is the head of the Astrophysics Research Group. She is a member of the Brazilian Academy of Sciences, and in 2015 won the L'Oreal UNESCO International Award for Women in Science for her work on the study of the interplay. Am I heard okay?
Yeah.
Okay. For her work on the study of the interplay between supermassive black holes and their host galaxies, which is still the main subject of her studies, she is widely renowned and respected as an expert in this work. And she is a sometime visitor to the CFA and a regular collaborator with several members.
Okay, thank you. Thank you, Peter. I will share my screen now. Are you seeing my screen?
Yes.
Well, it's a pleasure to be back remotely to present some work that I'm doing now with my collaborators, which is the impact of ionized gas outflows on nearby Seyfert galaxies and QSO hosts. Now the phone rang. Okay. So these studies that I'm going to show were made mostly with Gemini IFUs and with a collaboration of many people. Some of them are here. And I wrote a little bit of an overview, but I realized that maybe I thought I would have more time because this is too much. So I'm going to talk about motivation, calculation, mass outflow rates and powers. Maybe I go directly to the nearby QSOs and conclusions then. Well, everything begins with the feeding of the supermassive black hole. And I just want to make a little bit of an advertisement here of a review that I wrote with Schnorr Miller for Nature Astronomy about the feeding of supermassive black holes from 10 kiloparsecs extragalactic scales down to the inner parsec. So if you want to read this, or if you want to give to a student, maybe it's a good introduction to this field, and it's a review. Going to the outflows, the motivation to study outflows. We know that in order to reproduce the galaxy's luminosity function, we need some negative feedback, otherwise the models would produce too much massive galaxies and too much low mass galaxies. So the feedback from active galactic nuclei, outflows, jets, radiation, are put in models to avoid the building of too big, the galaxies to get too big, okay? And reproduce the luminosity function. So there are several models that use feedback recipes, and but still the observational side is not well constrained. So it's important to do more observation of these feedback processes. And one important number here that has the contribution from Martin Elvis, this paper of Hopkins and Elvis, pointing out that if you the feedback would be important in the galaxy if the power of the outflow, for example, is at least 0.5% of the AGN luminosity. So if you have an AGN, it will have a feedback that is powerful enough to cause some effect on the evolution of the galaxy, to influence the evolution of the galaxy. This power has to be at least 0.5% of the AGN luminosity. Okay, so how we calculate these feedback powers, and in the case of outflows in particular. So the mechanical power of the outflow is very simple to calculate. It's simple to calculate as in this expression. Then we need to calculate the power of the outflow, kinetic power of the outflow. We need the mass outflow rate. And then you need the mass, velocity, and radius where you are observing the outflow. Then the problems begin that in order to calculate the mass outflow rate, you need to have a velocity, and there are several uncertainties in the velocity. What velocity do you use? The peak velocity, the 95% velocity, which is the velocity corresponding to the wing of an emission line, or a width of an emission line. Also, the orientation of the outflow. You are not, you cannot know for sure which is the orientation of the outflow. So you are seeing just a line of sight component of the velocity. And then when you calculate also the mass of the gas is proportional to the H alpha luminosity. Usually we use H alpha, inversely proportional to the density of the gas. And then the density of the gas has many uncertainties because you have several indicators, but to be sure which is the density of the gas that is outflowing, it's a problem. And also separating which is the gas that is outflowing from the rest of the gas. We usually observe both the gas that is outflowing together with gas that's in orbit in the galaxy, for example. So I'm going to pass quickly, let's see, to some examples of these measurements. One is this 3C33, a radio galaxy. We are looking at the inner galaxy to see if you see some impact in the gas in the inner region. So we observe it with GMOS IFU. This is an HST image of the O3 emission line. And it's interesting that the emission, the line emission is not aligned with the jet. But the most interesting thing that I would like to point out that in this radio galaxy, we found two components in the inner region. And one component is the broad component. We found a broad component and a narrow component. A narrow component seemed to show mostly rotation in the north-south direction, no, in this vertical direction. And while the broad component seemed to be mapping gas perpendicular to the radio jets. So, so we identified that possible outflow, possible impact would be related to this broader component. And this broader component is showing an outflow, not along the jet, but perpendicular to the jet, that we call it equatorial outflow. So this equatorial outflow we have seen in other sources. This is another example we just published with collaboration with Aneta. This is Aneta's Galaxy 4C plus 29 that she worked a lot on this galaxy, and we did the IFU as well, and we found an outflow. And in this case, it's the only case in the radio galaxy that we have studied so far that we find a very large mass outflow rate. This is an interacting galaxy, and a large power with a large uncertainty, but the median or average value is 6% of the luminosity of the AGN. So this one is very powerful, much larger than the 0.5% that is suggested by models to be effective in the galaxy. I will not discuss these studies that are long lead, but maybe quickly to say that in these studies, our collaborators, Crenshaw, Rewalski, Fisher, calculated the mass outflow rates and kinetic energy of the outflow as a function of distance from the nucleus. And this is done using photoionization modeling. And then the gas density is obtained from photoionization models. And this is, I consider, a robust way to obtain the gas density. And in the case of the most luminous galaxy, Markarian 34, the kinetic power of the outflow reaches barely the limit of 0.5% of the AGN luminosity. So in this galaxy, the power is enough to impact the galaxy. In the others, the power is lower. I will go to the next paper because, well, just maybe show here in a paper of where we are studying outflows in a sample of 30 nearby AGN. We have found also 7 cases where we see an increase of the velocity dispersion. In this case, we measured W80 perpendicularly to the ionization axis. So we have found also equatorial outflows. Let me go back to show here this slide that in this case, for example, use the velocity as the width of the line divided by 2, the width at 80% of the flux. So it's a way to calculate the velocity of the outflow. We use the gas density obtained from the sulfur lines. And we consider that the gas was in outflow if this width was larger than 600 kilometers per second. So in this work, we have obtained very scattered position of these outflows. To summarize, we had only in 2 sources we had the power being close to 2.5%. Okay, I want to dedicate more time now for these quasars that are more luminous AGN that I was expecting to have a more powerful feedback from the AGN. And this is, you can compare here, this is the continuum image that showed the stars. We can see that is apparently an interaction going on here. And this is the emission line gas in O3 that we got. These are HST images from a paper of in 2018 with some collaborators from there. So we observed these 9 QSOs with very extended gas emission that has a bipolar morphology. We saw ionization cones in excitation maps, and we obtained ionized gas mass up to 2 times 10 to the 8 solar masses. And we use it because this was only an image study. We used the Sloan Digital Sky Survey spectra to obtain the velocities. And I want to summarize here that using our recipes to outflow, we obtained a range of outflows that was from 10 to -5 to 10 to -2 of the AGN luminosity. Okay, so it's a big range, but it's still a bit short. Only in one source we arrive at 1% of the AGN luminosity. Okay, so but then we considered, in order to get a very powerful outflow, we used another methodology used in the past by Liu et al., where they considered a spherical outflow. And then they just use this expression, the density, now it's proportional to the density, but then they use a very small density because actually this density should be multiplied by the filling factor. Okay, and then assuming a spherical outflow. Then we get very powerful outflows, 100 up to 100 times higher than using the expressions that I mentioned before. But note that this is not the mass of the gas is not well constrained because it's not using the luminosity of the gas. So it's made assumptions for the filling factors, for the density of the gas, and assuming also a spherical outflow. So what I wanted to say here, the message I would like to convey about this study is that you can have a range, a variation of 4 orders of magnitude in the outflow power, depending on the method you use to calculate it. Okay, so this is very impressive. And now I would like to talk about the work from Bruno, that is doing now the follow-up study of these QSOs using GMOS IFU. And the field of view is here in green. And these are the images of the sample galaxies showing the O3 emission, the very extended O3 emission. Okay. So what the spectra of the GMOS IFU show is that in most cases, I think in all cases, we can find a broad component most of the time in blue shift in the O3 lines. In this case, for example, in this galaxy, we have 2 narrow components, one more or less, let's say, intermediate, and a broad component. And we are assuming that the outflow is traced by this broad component. So when we do the kinematics and obtain the maps of the kinematics, the flux in this left corner is the flux distribution, the velocity, and the sigma for the 3 components, the 2 narrows and the broad. You can see that the broad component is confined in the inner region, but in this case, the reach is almost 4 kiloparsec from the nucleus. And so the outflow would be in this region. All this gas beyond this region is gas that is not in outflow, in this assumption that the outflow is traced by the broken component. One thing that we are trying to do is try to get a better constraint on the gas density. So this figure shows in blue the sulfur doublet density derived from the sulfur doublet that is usually used. The blue is adding the broad and narrow components, because in the sulfur line sometimes it's not easy to separate the broad and narrow. So you can do this for the inner part a little bit, and then this is for the broad component only, the orange. And then we used also a model from Baron and Netzer, where they actually is the same as Crenshaw and collaborators uses, that to use photonization models to derive the density. Okay, so these points are from photonization modeling, so you can see that the density, the density increases towards the center. And we found out that in two galaxies of the sample, there is these argonium lines that should be a better trace of the density of the outflowing gas, because we are tracing the outflowing gas with O3. And the sulfur lines have lower ionization potential, and so they most probably come from a different region. So the argonium line should be, because the ionization potential is more similar to the O3, should be a better tracer. So we see that indeed, for the two cases we have these argonium lines, the density from the argonium lines seems to be higher than the density of the sulfur lines, but below the one from the photonization model. Okay, so, and then we calculated the mass outflow rates and powers. And in this case, to calculate as a function of distance from the nucleus in the concentric rings, we use these expressions. And we use for the outflow only the mass of the broad component. The densities for now we are using from the sulfur, and the velocity is the velocity from the wind. So we calculated this as a function of distance from the nucleus, and we find that the mass outflow rates decreases as the radius increases. The same with the power of the outflow. So these different colors are the calculations for each galaxy. And Bruno did a study here of if we called the method that I just told as the default method to calculate the power of the outflow. If we vary conditions of in the calculations, how the power varies. Okay, so if you add the narrow component to the broad component, then we will increase the power. There is a method here that I don't have time to explain, but for example, if you use a lower velocity, that's not the velocity in the wing, then we decrease the power. Then the effect of the inclination, it's very large. We don't know exactly which is the orientation of the outflow. So it's very large. We show here from 75 degrees, 15 degrees, the angle relative to the plane of the sky. And then if we use the density from photoionization modeling, actually from a recipe based on a photoionization model from this paper by Barron and Netzer, then we decrease. And this is compared with the density that we obtain from the argonium also. So we have at least an order or approximately an order of magnitude variation depending on the way that we calculate the outflow power. And this is putting together our data, which are the blue stars, with other data of other people that has done this kind of study before, from Shimizu, this dark red or brown. Barron and Netzer got very low values down here. We got a little bit lower than the values first obtained by Fiori, who did this fit. And so here we are. And Bruno put here some reference lines in the power of the outflow. If it is 5% or 0.5%, which is the limit that we are considering for the outflow to have an impact on the galaxy, we see that only one of our galaxies reaches this line of 0.5%. The others, and with the arrow bars, barely touch it, this line. Okay, so I'm almost ending. So what we have, a summary, what we have been finding in the nearby outflows. The geometry in 60% approximately is bipolar. In 20% is compact or not well defined. In 20% is equatorial. So we find these outflows that are perpendicular to the ionization axis or the presumed outflow. Frequently this is found in radial galaxies and galaxies that have a radial jet. And this equatorial outflow seems to be like expansion of the gas by the passage of the jet. These are the velocities, mass outflow rates up to a few solar masses per year. And the outflow power in 2/3 of the sample that we have studied so far is less than 0.5%, meaning that it has little effect on the galaxy. We find a very large extended nanoline region up to 80 kiloparsecs, all ionized by the AGN, but the outflow is more compact. Sometimes the outflow is only 20% of this extent, but up to 80%. And you find a correlation with the AGN luminosity when you consider a large range of luminosities. And to finalize, so what we conclude that different methods and assumptions used to calculate the powers lead to differences of 1 to 2 orders of magnitude. But we need to consider other possible sources of feedback. For example, X-rays. You guys are the experts. And I know maybe Peter have some ideas about this. And also, I did not consider the molecular gas, the cold molecular gas. from CO. ALM observations show some of these outflows, but there is this uncertainty of the alpha CO, right? And regarding the effects on the star formation rate, many papers have been finding that the star formation rate in AGN hosts seems to be enhanced and not quenched in luminous AGN. So it looks like the feedback, if present, is maybe delayed. It's not happening at the same time as the AGN is luminous. And well, there are some other considerations about radio, that the radio loud AGN usually are observed in lower star formation rate galaxies. And there is also the role of the positive feedback that have been observed in some sources, but I think we don't have any statistics so far. Okay, I think I finished. I hope I didn't extend it too much my time.
Great. Thank you, Taissa, for a great talk. We have time for questions. If anyone wants to put them in, either raise your hand in the participants window or put a request in the chat window. And there's still time on Taissa's schedule if you want to Zoom with her privately this afternoon. Bill, I think I saw your hand.
Hi, Taissa. I had some questions about the ones that you described as being equatorial versus bipolar.
Yeah.
Is there anything in the structure of the galaxy or the structure of the radio properties that tells that correlates with why it should be one and why it should be the other?
Yes, we found some indications that, for example, we see in 3C33, and it's perpendicular to the radio jet. And there is another Seyfert galaxy that is less luminous, but it also has a radio jet, and this equatorial outflow is perpendicular to the radio jet. So I think we have to take a look in the ones that we didn't look yet for the radio, because it looks like you maybe when you have a bubble of gas being launched as a radio jet, maybe if there is not too much gas in front of it, it will push the gas sideways. So I think this is one idea that I have, and I didn't check all the galaxies that we have seeing this, if this is the case for everyone, but for some it is.
So I have more questions if you don't have anybody else raising their hand.
Go right ahead, Bill.
I'm trying to, but I can't do it on this tiny screen.
Okay. Well, maybe you can wait until after Martin. So we'll do Martin, and then we'll come back to you.
That's fine.
Hi, Taissa.
Hi.
The large-scale gas at 80 kiloparsecs that is not an outflow, what do you have any idea what that might have come from? Well, it's way outside the galaxy, right?
Yes, it's way outside the galaxy. And I think that we have some indication these are galaxies in interaction. So I think that maybe, the interaction of the galaxy produced by tidal forces produces some gas that is spread among the galaxies. And then you have at the same time, the AGN is triggered, and then you have the ionization of the AGN going outwards and illuminating this gas. But the outflow itself, that is, it's restricted to the inner kiloparsecs, to the inner few kiloparsecs. So I think that this is one explanation possible. Sometimes we see the interaction. Sometimes it's not that clear, but I think in the most extended cases I'm trying to remember is there is a signature of interaction.
Nice.
Yeah, I was expecting when I saw these images from HST that the outflow powers would be immense. Yes. And then when we get the measurements, it's very restricted to the inner region.
Hi, Taissa. Sorry if I jump in.
No.
There was this plot where you showed different samples and your data, and there was a correlation of the lines of Outflow. Yeah.
Mhm.
And the orange stuff is from Fabrizio Fiore, right?
Yes. Uh-huh.
Now, those are systematically higher than your points. So
Yes.
you think that that sample is biased, and what could it be?
Yeah, it's I like very much this work by Fabrizio, because what he did, he collected from the literature all data from people calculating outflows, and from radio, from this one is from ionized gas, because we are doing ionized gas. So and then he calculated himself using the same methodology. Okay, so he forgot about what people have done and did himself the calculations using the same assumptions. So there are some questionable suppositions, like, you know, he used the same density for all the galaxy. So if I'm not mistaken, it's 200 200 particles per cubic centimeter. And so, but he tried to homogenize the data and built this relation. And so I think that he got a very good correlation, because he uses a very large luminosity range and uses the same method of calculation. But there are many people that criticize, think that he did a too much simplified calculation. And why it's upwards? Because he used this assumption of the density equal to 200. And now, for example, Baron and Netzer, ourselves, also people, Crenshaw, Kramer, and collaborators, realized that when you do a proper protonization modeling of the gas in outflow, the density is of the gas that is outflowing, when you have, you know, the O3 fluxes, the line ratios from O3 and other emission lines, you do the photonization modeling, the density is higher. Baron and Netzer argue that it's up to 10 to the 4th. We are getting up to 10 to the 3rd, maybe 2,000, 3,000, instead of 200. So as the density is in the denominator here of the mass outflow rate, then if you have a 10 times larger density, you have an order of magnitude lower value for the mass outflow rate. So I think this is the main factor that makes our points, and more or less like that, one order of magnitude below the heat from Fiore.
Thanks.
Okay.
All right. I think we've got time for maybe another question. We're over right now, but if Bill wants to ask another question, we'll do that before we stop recording.
That's okay.
Okay. All right. Well, thank you very much. And thank you all for coming. It's been a great Wednesday talk session.